So we continue today with a presentation of T2 symmetric spacetimes with weak regularity. And you may remember the last time we started the geometric formulation. So that's what we are going to do today, to complete the geometric formulation and then to express the Einstein equations in coordinates, choosing some admissible coordinates adapted to the symmetry assumptions and to the weak regularities that we have made. So, so I would like, before we start with the screen, I would like to remind you that on each slice of foliation that we are going to construct for these spacetimes, we have an induced metric and we have a second fundamental form. And the regularity of this quantity is rather low. The metric H is basically in H1 and K is basically in L2. Right? So that's the level of regularity that we have assumed. And more precisely, I explained last time that we should be using a frame where T is Tx, Y, theta is a frame which is induced by coordinates. So these vector fields commute, and this is quite convenient when you want to derive the equations. But when you want to state the regularities, this weak regularity, you cannot use this frame. You have to use a frame which is adapted to the symmetry, and which is a frame that I call Txyz. So Txyz is our adapted frame. And, and the connection between the two is that Z is defined to be theta plus some coefficient times capital X plus some scalar coefficient times capital Y, so that Z belongs to the orthogonal of X and Y. Okay. And of course, Z is not smooth. So you have to play, everything I'm writing now, takes care of these difficulties that you would like to use, I mean, a frame based on coordinates because that gives simpler algebraic formula. But in the same time, you have to express a regularity in a frame which is not regular. So this creates difficulties that we need to cope with. The definition of weakly regular manifolds was given, and that's roughly what I was actually going to tell you on the blackboard, that we have roughly like an L2 regularity here and, sorry, H1. Let me show the screen. So, right, so this is a page. This is a statement of the regularity for the metric, which we take to be H1, at least for the XY part here. And then we have a coefficient HZZ, which is only W11. Okay, and then we have some other regularity, and we have also a condition on the area of the orbits of symmetry, etc. Right? So I'm not repeating all the details, but this is roughly the structures that we had for the metric. And for the second fundamental form, we had this. So K is roughly like an L2 quantity. So you basically take a derivative out of what I wrote for the metric, and here you take L1. Okay? So, so we need to work with that, right? And the first step is, can we actually express the Einstein equations at this level of regularity? Of course, there is also, okay, discussion about the time, but you will see that if you don't remember, it will come again. Okay, so I already explained that the Christoffel symbols were ill-defined. So if you don't look at things carefully, it's not going to work easily. I already explained, so if you look at the screen, so I already explained this part of the construction about how you translate the regularity of the metric and second fundamental form in terms of the Christoffel symbols. So we did that. We computed the Christoffel symbols. we look at the regularity, and we found the regularity was the one that we had essentially in a tensor K, and so forth. And we started this part, right? So weak version of the Hamiltonian constraint. So that's what we are going to do now. In each case, either geometrically or in coordinates, we need to be able to write the Hamiltonian constraint. We need to write the momentum constraint. And we need to write the evolution equations for coming from the Einstein equations. Okay? So we have three sets, or I should say maybe two sets of equations for the constraints on each slice and for the evolution. So these equations will give you hyperbolic equations typically, and these will give you constraints. Some of them will be ODEs, in fact. Okay. So here we are, right? So we would like to define the Hamiltonian constraint. So I already indicated the strategy last time, which is here. So first we are going to define the Ricci component, RZZ, right? Then, and this is what we did actually. Last time we wrote that, okay? So we had a formula expressing the ZZ component of the Ricci curvature at this low level of regularity as a distribution by some formula involving one derivative of the Christoffel symbols, right? I will show you that in a second. And then what we do, we are going to use a Gauss equation corresponding to the T2 orbits in order to define the scalar curvature of the manifold. And of course, in the expression of the constraint, or the Hamiltonian constraint, you also have the second fundamental form, K. You have roughly like the L2 norm of K. But the L2 norm of K is not quite well defined, right? So we have to be careful about at each step to do that. Okay, so let me just show what we found last time. So last time we found this formula that RZZ, so for the slices, was z derivative of this contraction of gamma AZA. Then there were products, quadratic products. And we observed that the first term was actually a derivative of a bounded function. This was related to the trace, and that was a regularity condition that we put on our problem. And then we had products like this, where you can see that some of them are products of the form L infinity L1, so they are well defined, and some others are of the form L2 times L2, which are also well defined. Okay. So we see that we can define RZZ at this weak regularity level. And in addition, of course, this is not quite the formula that you would use, right, normally. So there was some calculation here taking into account some cancellations, and of course the fact that some were vanishing, but that's easy. But the main point was to understand that some terms that would be ill-defined if you don't do that have been cancelled, right? So this formula now, as it is written, makes sense. And of course, if you assume regularity, enough regularity, you recover what you knew from the beginning. Right? So it's completely consistent. Okay, now we continue. Now what we are doing now is to write the Gauss equation corresponding to the T2 orbits, right? So we look at the T2 orbits within the slice. So it's transverse to the blackboard, if you like. And we write this identity here. So on one side, you have the curvature of the T2 orbits, right? But they are flat. There is no curvature. There is no dependence in the x, y variables that we are using. So this is 0. And on the other side, you find the various quantities that are here. And this is an identity that makes sense for regular metrics, right? So it's just general algebraic identity. So I take this. I have taken into account that z was not a unit vector, so very often this is gone because z is unit, so you don't need to write this term. But here we need to do it. And I'm now using that, but with the following observations. This formula as it is will not make sense for us. First of all, because in this equation you have chi, so let me maybe go one set of equations down. So chi is a second fundamental form of the T2 orbits, right? We defined this earlier. So it appears here, right? RZZ3 was just, we just defined it, but we defined it only in a weak sense, right? So this is a distribution. But because we need to normalize this quantity by the norm of Z, and this is not smooth, and this quantity is a distribution, this is not very well defined. Right? So what we are going to do, we are going to remove, in some sense, this factor HZZ, which is only W11, by multiplying this equation and rewriting it in a different way. Okay? But algebraic, if everything is smooth, I'm just doing trivial calculations. But it's important when it is not smooth. So we do that, right? We remove this factor HZZ by multiplying this equation. And this is what we get, right? So we get the scalar curvature, and I put a W to mean that this is our definition in a weak sense now. And I just collected all the other terms. But now, of course, this is gone here. So this makes sense as a distribution with the previous formula. And you are left here with the norm of chi, but chi was taken to be in L2. And therefore, when you compute the norm, square, and the trace to the square, you get something which is in L1. Okay. So this is what we will take as a definition. And it's obvious that when everything is smooth, we have just defined a weighted quantity, a weighted scalar curvature by doing this. Now, we need more observations because we need the norm of k, right, to write the Hamiltonian constraint. But the norm of k, I mean, we need actually not the norm of k, which would not be well defined, right? If you compute the norm of that, of course, these terms are okay, they are in L2, but this is not L2, right? So you could not write that. But fortunately, it's not the norm of k square that we want to look at, but it is a difference with with a trace of k to the square. And so if you do the algebra, you realize that you can write this quantity as a trace in 2 dimensions, square, plus a product like this. So now this quantity here, so trace 2k is a sum of these 2 terms, right? And this is something that we have assumed to be in L infinity, to be bounded. That's one of the part of the definition I didn't recall, but this is part of our definition. So this trace term is bounded, and therefore, of course, it's clear that it makes sense. The first term makes sense. But the second term also makes sense. So this is bounded, but KZZ is only L1, right, according to the blackboard. And then you have KAB. So this means that you compute the norm only of the XY part of this second fundamental form. So it's a product of L2 quantities. And here also, this is L2 times something which is also well defined, right? L2 times L2. Okay. So the left-hand side does not make sense at the weak regularity level, but the right-hand side makes sense. So of course, I'm using the right-hand side, and if I collect everything, this is what I have obtained, right? So I have obtained that the weak version of the Hamiltonian constraint takes the following form. So R3, so this is our weighted scalar curvature. We have now this weight HZZ because we have weighted the scalar curvature. And what I put here is just a collection of all these terms here. Okay? And I need to do that because now this makes sense. As I said, it's L infinity square or L infinity L1 or L2 L2, but this left-hand side would not make sense. This is well defined as a distribution, and if you assume enough regularity, you of course recover what you knew before. Okay? And if you want the whole formula, you have to plug this definition of W3. I mean, the expression is given by that, which was on the previous screen, and RZZ3 was given by that on even the screen before. Okay, so we are done for this. Right? We have our statement in a weak sense at a very low regularity level. Okay, and if you have understood that, basically what I'm going now to do is to repeat similar ideas, but there will be some differences. The calculation will become more and more technical. So I'm not going to show the details, but just to outline how this should be done, and most importantly, to emphasize the results that we are getting. The weak version of the momentum constraints takes the following form. So we have actually three equations. The first one is like this. So you have the z derivative of the two trace of k. Then you have this contraction of the Christoffel symbols times kzz. So you remember that this contraction was L infinity, and kzz is only L1. And then you have terms that are all L2. So the whole part here belongs to L1 and is well defined, and the first part is a derivative of a bounded quantity. So this equation makes sense, right? Whether or not this is really the momentum constraint, of course you have to do the algebra to see it. But I claim that this is my definition for the weak version of the momentum constraint of the first one. And now I have two more equations, which now look like this. So hzz to the power 1/2, kaz, you take the derivative in terms of with respect to z. Now what you have here is something which is L2, right? So you get something which is only w minus 1, 2. So it's somehow less regular. I mean, it's a distribution anyway. And then you have a second term here, which is a product of this contraction of the gamma, which is L infinity, and then this term, which is a general term in the second fundamental form, which is in L2. So I take this as a definition, and I claim that when it is regular, enough regular, sufficiently regular, the definition that I'm proposing here corresponds to the usual definition. Okay. But I also claim that this makes sense at our level of regularity, and when you look at each term here, they have the regularities that, I mean, they make sense, right? They make sense, which is completely unclear in the beginning. And I will show you the outline of the proof of that, the derivation, and you will see that there are terms that would not be well defined if you don't do this, this algebra. I have a remark here to emphasize that the last two equations are weighted with this quantity, with this norm of the vector z, and the first equation has a different homogeneity. So it turns out to be, that's the way that it should be in order for these equations to make sense. Okay? So we are essentially done with these momentum equations, except that now I need to outline the proof of that, right? And show you what sort of terms come. But okay, some of the details, I mean, most of the details are actually on the screen. So you can, by yourself, you can repeat the calculations easily, but of course it's not easy to see it directly from the screen. So what I need to do for the first momentum equation, I need to compute the divergence of kjz. Right? So the first line is simply the definition of this divergence. Right. The second line is simply all the details. I mean, there are indices and summations here, so I just decompose in terms of the component for x and y and the component for z. Right? And then it turns out that a number of terms cancel out, so I'm happy with the last line here, which is the expression of the divergence of kjz. Then what? So of course we have used that some Christoffel symbols cancel. But most importantly, we have also taken into account that some very bad terms, so gamma z is in L1, kz is also in L1. This is really the worst term and the worst product. And this product turns out to occur twice, or at least an even number of times with opposite signs, so they just cancel, and you are happy with the result because they are gone, and now this makes sense, as I explained before. Okay. So that's, I mean, the story is really like that for a number of terms. You also need to use at the trace 2, the trace k minus a term kzz. This comes from the fact that we have a frame, the property of the frame. And now we get what we want, right? You have to compute this quantity here minus the gradient, I mean, the z derivative of trace k. Right? So everything is on the screen from what I said. Now, you do something similar for the other two momentum constraints corresponding to the symmetry orbits, right? So I don't think I need to explain much details, but of course the formula are much more complicated. But the story is essentially the same. So you realize that the product involving gamma z, which is in L1, and this time it turns out to be kaz, which is only in L2. So this product, which will be ill-defined, actually, if I don't want to go too fast, so you see that in fact this formula contains this product, right? So you're not done so easily as in the previous case, right? You write the expression and it doesn't seem to work at first because you do get a product which is ill-defined, L1, L2. If I would take this as a definition, it would not work. So this is what I do. I formally multiply the above equation by the norm of z, which is this quantity, hzz 1/2, and that makes a trick. Okay, so this will kill the term that would not make sense otherwise. Right. Okay, so you have to look at the algebra to realize that, but this is the reason, you know, by just doing the same computation, it does not work, but you modify by a suitable weight, and you realize that things start to make sense. Okay. Okay, so we are done with the geometric formulation of the Einstein constraints at our level of regularity. So now we have to discuss the evolution part, right? So these are other components of the Einstein tensor. So some components correspond to the constraints and some components correspond to the evolution. So now we do the evolution part. So we start over with a weakly regular T2 symmetric Lorentzian manifold. So as I defined before, with a regularity, weak regularity on the blackboard, plus some mild assumption in time. For the time derivative, essentially there is an L1 regularity which is assumed for the time derivative. Right? And so we proceed in a similar way by looking now at the Christoffel symbols, but now we look at them for the whole frame, I mean T, X, Y, Z. Right? So the formula are more complicated, especially because the frame is not induced by coordinates, right? So we need to work at the level of this adapted frame. So the formula are a little bit more complicated. But nevertheless, you can do the algebra use some orthogonality conditions that we have here. So, for instance, x, y are not orthogonal, to each other. I mean, this would be a restriction that we are not making here. So there are some assumptions, I mean, some condition of orthogonality that you have. You have some properties of commutation of the vector fields that you have. So you combine that in a natural way, and you end up with an analog of what we had before, right? So before I gave you the expression of the Christoffel symbols from our data, and here I do the same. So I give you the Christoffel symbols, now all the ones that contains a capital T or more, right? So you have, for instance, maybe I should write some of them on the blackboard, at least we get them. So for instance, in the first part of the calculation, I give you that. So 1 over n. So n is a lapse function, right? It's a lapse function of the foliation. And Kij is our second fundamental form. So it's and then we have other terms like t and z, which is obtained to be z of n over n. And then we have, let me see, gamma. Okay, I mean, the other one are not given so explicitly on this screen, but I'm going to show them in the next screen. Right. Okay, so you do this algebra, you get the Christoffel symbols, and the point now is the regularity. So this is actually a summary that is probably easier to read, right? So here you have everything. So gamma ABT is given by KAB normalized, etc., etc. Okay. So the details, I mean, of the algebra is always a bit heavy to present. So you don't need to remember all the formula to follow what I'm telling you. So you have some formula for the Christoffel symbols, and the point is the regularity, right? We always want to look at the regularity, and we wonder whether some quantities are well defined or not, and what we should do for them to be well defined. So this is what I take as a definition. I'm saying now that the weak version of the Christoffel symbols is given by this formula. Right? So again, you have to understand that I'm not defining the Christoffel symbols by the usual formula, because they may involve products that would be ill-defined. So I do the calculation for smooth metrics. I get some expressions, and then I decide that this will be my weak definition. Okay. So you have that on the screen, and of course we wonder what is the regularity of that. So you remember that before we had L2, L1, L infinity regularity, and this is again what we will obtain here. So some of these components turns out to be L1, right? And some of these reflect the fact that the time regularity was L1 or W11, so it's expected to recover many terms that are at the L1 integrability level. And we have some other components which are in L2, and now I should tell you more about them, which is now some properties like we had before. So you remember that we had, for instance, the trace, the contraction of gamma. We had a term like gamma A, Z, A, a term like this, that was more regular. Okay. Instead of being L1 or L2, it was L infinity. And so we have the same here. So this term is L infinity. Now we have the difference between two Christoffel symbols, which is also L infinity, and another difference, which is also L infinity. Okay. So this may seem mysterious put like this, but you will see in a second where it comes from, right? So of course, if you again assume that the space-time is regular enough, all the formulas that I'm writing coincide with the standard definitions. But they now make sense. Okay. So let me emphasize. So to illustrate this screen here, right? So I'm telling you that some component belongs to L1, some other component belongs to L2, and some contractions or differences like this are better behaved, right? So if I show you some formula for these quantities here in the second part of the screen, in terms of our data, the metric and the second fundamental form, and if I connect this with the time regularities that we have assumed, then you will see where these conditions come from. So this is what we do now. So the contraction gamma TAA, for instance, turns out to be the trace 2 of K, which we assume to be L infinity, right? So this is something, I mean, if you refer to these matrices here, they really, except that I didn't write all the details, but last time I did that in more details, but you can read off on these matrices the regularity of H and K, and what I'm translating are these regularity assumptions translated at the level of the Christoffel symbols. Okay. So this one is a trace 2, like written here. You may also remember that there was a conformal regularity condition that we have assumed. Okay. So I told you that, you will see that in a few minutes. We are going to solve wave equations. right? Wave equations with quadratic nonlinearities. And the wave equation will have a main operator containing this coefficient rho, this conformal metric coefficient. Right? And so I have assumed more regularity on this rho, at least W1 infinity, but in fact it was even more than that. It was W21 in the definition, but at this level for this argument to say that it is W1 infinity is enough. So, so we have put this assumption, right? Because this is the metric that comes in a wave equation, and there are many reasons to assume it to be more regular. I mean, we can prove that it is more regular. It's not really an assumption, that we prove that the Einstein equations are consistent with this conformal metric being W21, and for the purpose of this argument, W1 infinity will be enough. Okay, so this is something that we have assumed. Rho belongs to W1 infinity at least. Okay. And in fact, this condition precisely tells us that the difference between these two crystal symbols, if you do the algebra, is equal to a time derivative of rho minus 2, which we are taking to be bounded. Okay. And similarly, if you look at the difference between gamma ZZZ minus gamma TZT, you see that this quantity is a z derivative of rho squared, which has also been assumed to be bounded. Right? So the conformal metric is more regular than the rest of the coefficients. That's what we are doing here. Okay, so we proceed at this level of regularity, and now we express the Einstein evolution equations. So, of course, we only need, so probably most of you know that to find the evolution equation, what we need to do is we need to write the Rij, where Ij correspond to the indices of the slices of the foliation. So these components will give us the Einstein evolution equations. Okay, and so here I'm writing the formula, right? I will only sketch the proof of that, but you do the calculations again for the curvature in terms of the Christoffel symbols. And this is what you get. So you find that the ZZ component of the Ricci curvature is a time derivative of this component minus the Z derivative of this, minus the Z derivative of this trace. And so you see that the worst part will be the first term, which is only in L1. So when you differentiate, you will get only a distribution, a derivative of a function in L1. So that's definitely singular. And then you have terms for which I'm now going to use this additional regularities that I could prove, right? So I told you that these differences, this one and this one, were L infinity, were bounded functions. And that's useful because when you write the expression of the Ricci curvature, you collect the terms in this way, right? So you should not split this in two terms, right? Of course, for smooth solution, it would be possible. But this would make sense. It does make sense, but it makes sense only if you write it in the way that I wrote it. Okay? So first part is L1, and the second part is bounded. Structure is the same for the next term. And next line will be L infinity for this part, L1, and we have even more terms which are L2, L2, which are more regular. Okay. So all this hierarchy of structure, regularity, integrability, you know, has to be done. And this, so somehow there is something new here compared to what we have done before, right? So we found terms like this before. Meaning for the constraints, right? But for the evolution, there is something more where we need to collect two terms in this way in order to get something meaningful. So, of course, there are two more equations, a weak version of the components, of the Ricci components AZ of the Ricci tensor, and they take the following form. So RAZ is a T derivative of gamma T AZ. Again, you have to collect two terms. This is bounded, right? Each is not L infinity, but the difference is L infinity, right? So it makes sense when you do this multiplication, and again, you are here. Okay? So I'm done. Let me see. Okay, actually, I'm not done because there are more components to be expressed, but this is at least part of the story is given by that. But I need to continue for another page to now look at the components R, A, B, where A, B correspond to the components capital X, capital Y. But now this will need to be suitably weighted in a way that I'm now showing you. So again, I'm putting a W to express the fact that I'm not exactly working with a Ricci curvature, Ricci components, but some weighted form of them. And so this weighted form, weighted by something I will specify in a minute. I mean, you can guess what it is. It's essentially this coefficient. And so this weighted Ricci curvature component is a t derivative of gamma dc t, where this is the indices are dc or cd here. Then you have a z derivative of another gamma component, etc., and a lot of terms. And now these terms turns out to be all well defined, and it gives you a definition where you have a derivative of something in L2 plus a function which is in L1. Okay. So, I guess no, yeah, I mean, again, maybe the same remark here. So you should not split this. I mean, you could split that in two parts, right? This is a trace, so you could say, okay, I can write two terms for that. But if you write two terms and you separate the two terms, right, they would no longer make sense. Okay, and so we are now done with writing the evolution equations for Ricci flat spacetimes. We have defined RZZ. We have a formula for that, right? So if I want to write the equation in a vacuum, I would require that RZZ should be 0 in a sense of distributions, and the same for RZD and RAB with this weight. Okay. So what I didn't show, but I can show that. Okay, let me return to this in a second. But that is a derivation, right, of these equations that I show you. So let me just give you the flavor of the arguments, right? So it's somehow the same story that you repeat for these evolution equations, the derivation of the weak form of the evolution equations. So you can see on the screen that you start with a basic formula, and then you express all the terms, and then you start collecting some terms and using properties of commutators and orthogonality and etc. Right? And after maybe another page or two, you realize that there are again some constellations of products like this that would be ill-defined at a weak regularity level. So you cannot keep them. And so you hope for them to cancel or to be grouped together so that the sum or the difference of some terms would start to make sense. So that's what I have done here. And this formula is a formula that I just showed you before, but this is a detailed of the calculations. And then you look for another component and you do the same. You have a big formula and you realize that some terms are 0, so that's rather good. But that's not enough, and you need to realize that some ill-defined terms like those cancel, and in order to get the final identity, which is again an identity that I show you. Okay, so let me just go back to the conclusion for this section. So the conclusion here is that we have found a way to define the Einstein equations in a weak sense at the H1 regularity level. That's basically our level of regularity. And we can, therefore, we have a definition which is consistent with the one that was known before for smooth metrics. So if you give me a regular T2 symmetric spacetime, what I call the weak version of the Einstein's evolution equations and also the constraint is satisfied if and only if the same thing they are satisfied in a classical sense. Okay. so here we are, right? So that's basically the statement. And so what we have now, we can use this terminology, weakly regular T2 symmetry initial data set. That's completely defined, but it was not defined before, right? Before I was defining, I didn't define the Einstein constraints yet, but this now is done. And I can also talk about the weakly regular T2 symmetric Ricci flat spacetimes. And so what will be the objective now? It will be to go to the second step here, to formulate in coordinates, what I will call admissible coordinates, these equations in a weak sense. Okay. And you will see the PDEs, the hyperbolic PDEs to appear. Okay, so let's do that. So these are just the calculations that I sketch. In fact, before I can do that, I have to talk about the twist coefficients, right? So what I skipped were just calculations that you may read if you want to see more details, but they are not difficult. Okay, so before actually we do that, the coordinates, I have to tell you about something very important that some of you know, these twist coefficients. Okay, so the T2 symmetric spacetimes have some equations, because, I mean, out of what I wrote, you will see, you get plenty of equations, right? So if you want to be able to solve them at some point, it would be nice to have some a priori information about, about these equations. So the twist coefficients are allowing you to actually remove 4 equations, basically, in this list. So 4 equations would be very simple. But they would be very simple if you go through the next 2 pages. So it goes like this. You look at your Killing fields, x, y, and you compute the derivative of one of them, or one or the other, and you contract that in some way using the volume form. Okay. So this is a quantity you compute, epsilon, alpha, beta, gamma, delta. Epsilon is a volume form on your manifold, and you contract the vector fields, your Killing fields, and the derivative in a certain way. So there are 2 different ways you could do that, and so I call this Cx and Cy. These are scalar quantities defined on the spacetime, right? Maybe not; they will turn out to be constants, but at this moment we just know they are functions on the manifold. And with a weak regularity, we actually, because I didn't define the connection directly, so I prefer to see that in terms of the Christoffel symbols, but that's just the same, right? So some quantities, some combination of the Christoffel symbols and the components of the vector fields are introduced. They are called Cx and Cy, and we always work within this frame. Okay, so the first observation is to wonder whether they make sense or not. But in fact, they make sense because they only involve product L infinity L1 or L2 L2, right? But you have to look a bit carefully at that to see it. But they do make sense. Okay, they do make sense, and they are actually L1 functions in your manifold. Okay. And so this is a lemma that we want. The twist coefficients of any weakly regular T2 symmetric Ricci flat spacetime are constants. That's what I was saying. And moreover, we can always choose the Killing fields by doing some linear combination in such a way that one of them will vanish. So you can make this Cx, for instance, to be 0, and Cy would be a non-vanishing constant. Or it could be vanishing, but this would be a special case of a subclass of these spacetimes, which are called the Gaudi spacetimes. Okay. So this, this property answers this question. I mean, in this big system of equations, are we going to be able to do something? And by using this observation that we can simplify some of the equations, we'll be able to proceed. Okay, the proof of that is not difficult, but it requires some calculations, which I will sketch here. So the first line is simply the formula, right? The formula that we had here, and then you look at all these possibilities for the indices, alpha, beta, gamma, delta. And you realize that many of them are zero because epsilon is a volume form. So you have to pick up 4 different vectors in order to get something non-vanishing, right? So you get only 2 terms which are non-vanishing. And in view of some relation, so this is something that I can deduce from the expression of the gamma that I gave you before, right? So there is some relation. So I'm going to use this relation here. This is simply the definition of the lapse function, which is the norm of the capital T vector. And this becomes this quantity here, just twice the same quantity. Okay. And now the volume form can be expressed by returning to the expression for the metric. And you see easily that you can connect the volume form with the lapse function, with the norm of Z, and with the area of the orbits of symmetry. Rho defined by that, this is a definition that I already gave before. And so in the end, that's what you get. Okay? So this what will be the twist constant is actually a Christoffel symbol multiplied by the area over this conformal coefficient. So it's a very neat formula. So far this is just some elementary algebra. But now the important point is that this Cx is a constant. Okay. So to do that, you have to do some additional calculations. So maybe I will skip that and not show you the details of the next page. But you can prove now that you have this formula here. And we have these Einstein equations that indeed involve T derivatives or Z derivatives of this Christoffel symbol. So it's clear that there is a possibility that we could write a nice equation on this. And the nice equation is simply that this quantity T of Cx is 0 and Z of Cx is equal to 0. Okay, so they are very simple. They give you quantities that you can integrate out, and you can simplify very much your system. Okay, and the fact that one of the twists can be made to vanish, the reason is that. So you can introduce a linear combination of the two killing fields. So you have 2 killing fields x and y. You multiply, you do this, right? Ax plus by, and y prime is defined to be Cx plus dy. You want to preserve the area of the orbits of symmetry, so you impose this condition here. And you compute how these Cx, Cy are changing according to this transformation. And they change in this rather simple way. So you have AD minus BC, but this is 1, so it would not contribute. But what is important is that by doing a linear combination of the 2 killing fields, what you have done is you have done a linear combination of the twist constant, right? So now you can easily choose A to be the ratio of Cx over, or Cy over Cx minus that, or something like this. And you arrange that one of them would be 0, and the other one may be non-vanishing. Okay, so if I skip that, it's probably biased. But the interesting part in this calculation is a regularity. So of course you have to be careful about using arguments that are only using the regularities that you assume, right? And that's indeed the case. So when I do this calculation and I want to compute T of Cx, so I start with one of the Einstein equations. This component Rxz is equal to 0. And I get an equation which is not quite what I want, so I get an equation like this. And so to proceed and obtain the conclusion, in the middle of the proof, I need to use that rho is W21, T of rho is W11, in order to fully justify the calculations. Okay? But these calculations, they are valid at the weak regularity levels that we are assuming. Okay, so we are done with the first part of this lecture. And I will now begin the discussion of the formulation in admissible coordinates. So for the regularity in coordinates, so we start like before with a weakly regular T2 symmetric Riemannian manifold. And we take our functions that are defined on each slice of the foliation. Because of the symmetry assumption that we are making, we can reduce the problem to functions that are defined on S1. The invariance under the T2 action allows us to do that. So we will actually write a problem. We'll write PDEs that contain the time variable and one space variable that describe S1. Okay, so that's the goal. We do that by using an adapted frame like I have explained a couple of times. And what I will call the admissible coordinates are these coordinates x, y, z, such that, so x, I mean capital X, capital Y, capital theta, sorry, the coordinates are x, y, theta. Right? There's no z in the problem. So this is a basis of vector fields which is induced by coordinates on T3. So I think the setup is clear. And the first step is to express the metric in these coordinates. Okay. Okay, so let me write the expression for the metric. So the metric on the slice, so H will be given in this form. E2 nu, maybe I remove the bar on the blackboard, but that's the same thing, over R d theta squared plus E2p R, and then we have G d theta plus dx a dy square. Okay, and I think we have one more term, which is E minus 2p R bar H bar d theta plus dy to the square. Okay, so this is going to be the formula, the expression for the metric in coordinates. So it depends on 6 coefficients, right? R, this is the area of the orbits of symmetry. So this will be one of the unknowns in this formulation. Then we have 2 coefficients, P and A, that will satisfy wave equations. So P and A are really the main, I mean, they contain the main dynamics, gravitational waves that we were talking about in the beginning. And then nu is also some important coefficient, and G and H are not important. I mean, they will satisfy very simple equations. Okay. So the main part will be described, the main evolution equations will be given by the evolution of A and P. So on that, we will get wave equations. And that's what we will be doing here. So, okay, so the metric takes a form, which I wrote here. So, of course, I need to explain why we have that, right? So I do that in a second, but now I just show you how it looks like. So again, you have the area of the orbits of symmetry. So for instance, if you compute, you can check easily that if you compute the determinant of the xy part of it, you will see that the E minus 2p will cancel with E2p here. Right? So these two quantities cancel out, and you see more or less directly that you will get R, you will get the product of R square, and this is the area of the orbits of symmetry. This is the part that give you how the T2 orbits, the area of them. Okay, now, maybe before I proceed, I just want to show you maybe the first line in the next screen. So any metric can be expressed in this form. So what I've done here, I've not made any assumption, right? I take a metric which has a T2 symmetry. So my coefficients are going to be independent of x and y. They only depend on theta in this case. Just for the slices, it's really they are function of theta. Theta is in S1. And this is always possible because you can simply express a metric in a very general form and solve for that. So you just express that x, you know, it's really, I mean, it only means that I'm taking this matrix here, and I have 6 coefficients because this is symmetric. But these 6 coefficients, I want to take them in a special form because this is going to be convenient for the analysis. I mean, even essential, not only convenient. Okay, so I can always do that. So what's important now is to understand how you translate the regularity that was assumed geometrically, how you translate this regularity in terms of these coefficients. Okay. And that's what I've done here. So P and A belongs to H1. So maybe I will keep this on the blackboard. So these 2 coefficients will belong to H1. They will satisfy these wave equations. Then you have one coefficient nu, which will be in W11 of S1. And you will have the area of the orbits of symmetry, which will be a Lipschitz continuous function on S1. And you have 2 more quantities, which, as I said, are not that important, capital G, capital H, which are assumed to be in infinity. Okay? So first line is a general form of the metric, right? And the final part of the screen is a translation of the geometric regularity in terms of the metric coefficients. Okay. So I need to explain a little bit that, and I do it by computing that. So for instance, for the area, we have assumed that the area was Lipschitz continuous. This was our assumption geometrically. It was in principle defined on T3, but we can identify this R bar and all the other coefficients of the metric with functions defined on S1 because of the symmetry. And therefore, we do get that R bar is Lipschitz continuous. So that's easy. Now, the component HXX is in H1. That's something that you can read on the blackboard here. Right? This component here belongs to H11. So let's look at the metric. And you look at the metric here, and you compute the expression of HXX. Right? So it's E2P R bar. So this is really the coefficient that you find from out of here, right? E2P times R dx squared. So this is my coefficient HXX. This is in H1, and therefore, what do I get? So I get that because R bar is more regular. It has a derivative which is bounded, right? So if R bar has a derivative bounded, and you get that E2P belongs to H1. And again, if you identify functions on T3 to functions on S1, you obtain that this quantity here belongs to H1. Okay. So that's not yet what we want. But now we continue because it is in H1 and defined on a circle. It's a continuous function. It is also positive. It's defined on a compact set S1. And therefore, we can define the inverse E minus 2P, which is also continuous. And it follows that you can now compute the theta derivative of P. You write it like this. I mean, I'm really saying something rather easy here, that if I know that a combination E2P is in H1, then P itself is in H1. Okay? So that's what I'm saying here. P belongs to H1. Okay? And that's one regularity condition that we wanted to achieve. The argument for A is similar. And we can continue with now some additional components. If you look at the components now, HXZ, so it's one other component. It's basically this product here. So G plus AH multiplied by E2P times R. But we already know that, you know, these two quantities are already known to be bounded, right? So what you get out of that is that G plus AH belongs to L infinity. Okay. Okay, and you also look at the component HYZ, which is a bit more messy, which is L infinity. And you already know, I mean, I'm just expressing the regularity of each component and translating what it means on the metric coefficients. Right? So this guy has already appeared in a previous line, so I already know it's bounded, and therefore I get that the second part is bounded. Right? And now you have already a bound on R, so you get that the remaining term is L infinity, and you get that H bar is an L infinity, you return to the step before, and you also deduce that G bar is L infinity. Okay. So there is some, you know, some algebra like this that you have to do. And maybe the final component is a HZZ component. So you remember that this is really the worst one, so you have to be careful about it. You remember that Z was in the orthogonal defined like that. Defined by projection in this way. And so if you compute HZZ from the metric, so HZZ is not quite H theta theta. There is a correction that is given by that. It is computed to be this. And if we know that HZZ belongs to W11, what it means, because we already know that R is Lipschitz, right? R is the most regular quantity. P is H1. So these two are already under control. So you look at the last remaining quantity, which is this nu bar, and you obtain that nu bar has a regularity of what you have assumed on HZZ, which is W11. Okay. So I gave you the argument for this lemma, and right, so we have that. Okay. Now we can repeat this discussion not for the metric, not for this induced metric, but for the second fundamental form. Okay. And the story is essentially the same, right? So instead of having a regularity which is H1, you have a regularity which is L2, but you can do the same. Have a decomposition of K and express that the coefficients are in L2 or in L1 and see what it means on the components in coordinates of the second fundamental form. Okay? So let me show you the formula by this. So don't be afraid by it. It looks a bit ugly, but it's not that bad. So you have 6 components, right? So KAB is given by that. So I first look at this part here, right? So this part of the second fundamental form is given by the first line here. So there is a factor here which will turn out to essentially to be 1 for one choice of coordinates. So this is not very important. So I'm basically telling you that this second fundamental form is equal to HAB, and I put a 0 below because for me this 0 stands for a time derivative. Okay. So for instance, think of R bar with a 0 with a factor here to be the time derivative of the area. Okay. That's what the second fundamental form should be, right? It's a time derivative of the metric, if you like, the metric quantities. Okay. So that's what this decomposition is telling you. But view really this decomposition in a similar way as here. I have a tensor. I want to express it in some coordinates, so I introduce some coefficients. It's just that the coefficients cannot be introduced randomly, otherwise you would not be able to read the regularity on these coefficients. Okay? So you have to take a certain form, and this form is completely justified by the fact that we want to think of K as a time derivative of the metric, right? Roughly speaking. So this is what this is telling you. okay, so if we want to enter a little bit more in the formula, I mean, we can go through it, but this will not be very important for the rest of the discussion. I will not emphasize, focus on this part. So I just want to emphasize a few things in the screen. First of all, the regularity. So again, the PA component, and this stands for the time derivative, if you like, of the PA. That was H1 here. P and A were in H1, so their time derivative are expected to be in L2. And this is what I assume geometrically, this is what I get at the level of the coordinates. The time derivative of R is bounded, and the new time derivative of nu is L1, right? So you can really expect everything I'm writing here is completely expected from the previous result. Okay. Even though the algebra is a little bit complicated. Okay, so we should probably make a break. So let's make a break now, and after the break, I will just add the lapse function, so to the story. We have to just add this term, so not too much to be said. And then we will be ready to write the Einstein equations, and you will see the PDEs that we need to solve. And today we will finish the discussion of the formulation in coordinates. We see the set of PDEs, and next time we will see how to solve this system. Okay. I can now show you the set of PDEs, right, that you have all been expecting, hoping for. So now we have a space-time metric given in this form. So of course the special part has not changed like before. It depends on these coefficients, R, P, A, nu, G, and H. And now for the time part, you remember the form that we had assumed for the metric. And so we had this additional term minus n squared dt squared, where n is called the lapse function. The regularity for P and A is that, so belongs to H1. And the time now, it depends on time as well. And the time dependence is at this level, it's just that it is bounded in locally, at least in this interval of definition of the time, capital I. The theta variable is in S1. And nu, so the lapse function and the function nu that we already had before, they now are quantities depending on time. They belong to W11. G and H belongs to L infinity, and R belongs to W1 infinity in space, and it is bounded or locally bounded in time. Now we need to say something more about the regularity in time, right? The derivative in time that we could not see when we were only looking at a slice. So in terms of time derivatives, we have what I've stated here. So the time derivative of P and A belongs to L2. This is consistent with P and A being in H1. We have nu sub t, which is in L1, and this is consistent with nu being in W11. And we have two more properties here about the area. So if you differentiate the area function in time, you get a bounded function. And this is consistent with this Lipschitz property of in space. And G sub t, H sub t belongs to L2 in space. Okay. So these conditions, of course, are simply the translation of the geometrical regularities that we assumed in our definition of weakly regular spacetimes. The detail of that is given by this calculation. So you look at the KZZ component, which we know is in L1. This is, again, on the blackboard. You can see it. And you look at the component KZZ, and we saw before that this was a time derivative of one component of the metric. And that's what I wrote here, time derivative of one component of the metric. You can expand that and compute this out, which I will do now to obtain the regularity of each coefficient in time. But before looking at that, you have the other expressions for the second fundamental form. So you have all the components of K. and they all appear as time derivative of some corresponding components of the metric, right? So, so the trace 2 is given by this, and that's now from these formulas. From that I'm going to deduce a regularity in time. Okay, and so for instance, you know that k, xx, xy, yy was in L2, right? So that was the first part here of k. So this part here is in L2, and what it tells us here is that, for instance, for kxx, you go here, so E2p times r should be, and also that similar quantity that comes from here, and so forth. So these two quantities, for instance, you get them in this component kxx and in this component kyy. So they have to be in L2, and it you know, you translate what it means. So it's really the same story as what we have done for the metric that you repeat for the second fundamental form. You have some regularity for k, geometric regularity, and you wonder what it means at the level of the coefficients. Okay, so you can go through all of that. The trace 2k is a time derivative, and so on and so forth. It's really straightforward from this formula. Okay, so let me repeat by showing maybe the statement. So we have a metric, and this is what we will do now. We have this metric decomposed in this form. We have coefficients that are either h1 or w11 or L infinity or w1 infinity. So this is our metric, and we would like now to express the Einstein equations in coordinates, in these coordinates, these adapted coordinates. So we proceed with some more calculations. You remember that the scalar curvature has a weight, and it was defined by this relation here, and you know, and this is the details of that. So this is a formula that we had found before to define the weighted scalar curvature, and we need now to compute. So how do we use that, right? How do we use that? So we use that because by writing explicitly the Christoffel symbols, and we had the formula already given before, and we also need to compute this second fundamental form of the T2 slices in the T3 slices. Right? So this chi here is something that we have not computed yet. It was defined by this formula, and so we need to compute more. But intuitively, you know, this chi, it tells you how the T2 slices are curved in the T3 slices, right? The T2 orbits in the T3 slices. So all these formula are always the same. They correspond to a z derivative, you know, normal derivative of the metrics that you have on these slices. Right? So after you have understood, if you are not familiar with that, if you understand one or two formula, you will realize that they all look the same. Okay. So I don't want to go through the details of the calculations, but if you want, most of the calculations are written on the screen and on the notes that I will distribute. And so on and so forth. You continue with some more calculations, and you arrive to what you want to see, right? So this is our first equation. So they are actually quite long, so I'm not going to write them completely on the blackboard, but just keep the main outline of that. So we have one equation that corresponds to R weighted for the three slices, and they look like that, right? So they contain the theta derivative of the area over R, and you again differentiate in theta. So this is second order in theta. And this is okay, this is the term that contains the largest number of derivatives. Okay, so schematically, you can just say that you have a term like this, and the other terms are lower order. Of course, this is not the final formula, because, okay, sorry, so I'm not at the end of the calculation here, because what I did here did not include the variation. So this was a chi that came from chi. Chi was the z variation of the induced metric on the two T2 orbits, and there was a norm of it. So there is still one term that needs to be computed, right? Okay, so this is not the final formula, but if you compute that variation of the two metric, you look at the second fundamental form of these T2 orbits, and you want to evaluate this quantity. This quantity is only L1, right? It's a product. It contains products of L2 quantities. So there's more algebra, but it really, for the discussion now, it doesn't matter the details of that. And I only want to look at the final formulation and get a set of PDEs that we want to solve. Okay, so what I was going to say is still correct, but now out of this formula, which seems now to be the final one. So this is really a PDE for the functions that we had. So we had a P, an A, PA, we had a nu, R, and G, and H. Okay, so this was the coefficients of the metric. And so now I have found one equation. So these components here produce an equation which is of this form. So there are lower order terms here equal to 0. Okay. Now let's continue with the next calculation. Now we need to derive the Hamiltonian equation. So we need to compute. Yeah, actually, I'm really not. Okay, I go a little bit too fast in explaining things because this is still not the final equation, because we have not taken the second fundamental form into account. Okay, so there is. Okay, so the full equation that I really would like to write on the blackboard, of course, contains also the norm of capital K square and this quantity here. So there are still more terms to be computed. Don't try to go through the details on the screen, but please look at them afterwards if you wish. And after now some more work, we are indeed where I wanted to arrive. So we do have the Hamiltonian constraint. Okay, which has this form. So it's indeed, maybe I can just forget about this -2, it's irrelevant. So I have a quantity like r theta over r theta derivative. And if you look at the next terms, they will be product of first order derivatives, or it would be a square of r theta to the square, or r sub t to the square. Look at the other quantities, they have the same flavor. And so the only thing I need to say is that this is an equation that we have been able to define in W minus 1 infinity. Okay. So this first equation is defined in W minus 1 infinity according to on the slides, and this was according to our geometric definition. This equation makes sense in W minus 1 infinity. I could probably say immediately that this equation implies some additional regularity that we didn't assume, we didn't have before. Which regularity? Simply because only one term contains two derivatives, the first one, right? All the other ones contain only one derivative. And for terms with one derivative, you know that these quantities are L1, L2, L infinity. So if you look carefully, you realize that this whole quantity is nothing more than being L1, but only one term contains two derivatives. So what I want to conclude also, in addition to having this first Einstein equation, I can also conclude that the theta derivative of the area is in fact more regular than what we expected, right? Now, for the momentum constraints, we proceed by first looking at the direction of the T2 orbits. The equation that we had derived before actually can be put in a very simple form, this form. And it has two, A goes from, it can be capital X or capital Y. So this is an equation that lives on the T2 orbits. And we, so it's simply if we look at our decomposition of the second fundamental form that I show, right, in coordinates, what this means in coordinates, it means two equations which are quite simple because they tell you that some algebraic quantity of the time derivatives of g and h and the algebraic metric coefficient, so some combination of that is constant in theta, and here a similar quantity is also constant in theta. Okay. So these are two components. The weak version, so it's very much connected with the twist equations that I mentioned before. Actually, these are the statements that the twist quantities are independent of theta. But you can also see them as being the momentum constraints in the direction of the T2 orbits. Okay, so to that, I'm going to add these momentum constraints in a T2 direction. Okay, so maybe again, I just want to write this schematically. So you have a conserved quantity in theta and another conserved quantity in theta. Okay. Now we can also look at the momentum constraint in a z direction. So we start from our geometric definition, which was that z of the trace 2 of k and some combination, and you remember that there was some regularity here and you had to be careful about defining that. So this is our statement, our geometric statement, independent of coordinates, and you express this in the coordinates in a following way. So you look at the z trace 2. So I already wrote this before. So the trace of k on the orbits, I already told you that this was a time derivative of r multiplied by a certain coefficient. And so you expand this. You have z of a product, and you expand this, and et cetera, et cetera. So it's a bit heavy, but you also compute, okay, some other terms. So I skip again the calculations that are not essential for understanding the ideas. There are even more terms to be computed, but eventually, this is what you get. So you have now the momentum equation in the z direction, and it looks like this. So you have this r bar 0 quantity. So you can think of it as a time derivative, and you differentiate this with respect to theta. And again, you can consider that this is the most singular term. Okay, so there are lower order terms equal 0, and this is an equation that we define in W minus 1 infinity of S1. And once more, as I mentioned before, you can derive additional regularities that this quantity R bar 0 is in fact, say, W11. Okay. Because all the terms that come here will be typically, I mean, there will be probably product L2, L2 or L1, L infinity, right? You have to look carefully at each term to realize that. But this is L1. So you get some additional regularity, and this is a philosophy that the Einstein constraints actually imply additional regularities that you didn't put in the definition, but they come from the equations. Now we move on to write the weak version of the evolution equations in admissible coordinates. We are given a weakly regular T2 symmetry Ricci flat spacetime with admissible coordinates. And we start with a Ricci component. So the Ricci component of this form. I mean, the Ricci component RAZ. So we have two components, RXZ and RYZ. In the Ricci flat case, they are just 0. And it turns out to be ODEs, in fact. So I'm continuing the list here of equations. So you have RXZ is equal to RYZ equals 0. So these two Einstein equations give you equation of this form. So you have rho. So you remember that this rho was a conformal factor in a metric. The area of the orbits of symmetry and E minus 2 nu and H sub t. So this is independent of time. And you have one more quantity which is also independent of time. So rho r squared E minus 2 nu plus 4p and gt plus a h t t. Okay. Look now at the next component. So RAB of the Ricci curvature. So that will give us now some important evolution equations. So again, you do the algebra, you compute what you have to compute, you start with a geometric formulation. So this is the first line, that's what we have adopted as our definition. And you express everything in the coordinates, right? So always the same thing. I have some geometric quantity, I express this in coordinates. And that's what you see here. You see that you have a metric and a z, blah, 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 and the g can be replaced by its expression from the coordinate decomposition, the metric in coordinates. Okay, and okay, it takes a little bit of work, but in the end, that's what you are getting. So the xx component is given by that, and this is one of the main equations. Actually, if you want to think in terms of gravitational waves, for instance, it would be driven by this equation. Okay, so this equation that we are getting now is second order. It corresponds to the component Rxx. It's a nonlinear wave equation for P. Okay, so maybe I don't write it, but you know, it looks like this. If you forget about the R contribution, it's really maybe let me just write a principal part on the blackboard. So it has this form, right? Rho p sub t minus rho minus 1 p theta, and there is another t here. And okay, and these are not quite lower order terms because you have also two derivatives of the area, but at least that's a main part of the equation. And depending on the precise gauge that you use, it may turn out to be exactly the principal part of the equation. So this equation is satisfied in W minus 1, 2. Right, so this quantity is Pt, P theta are L2, and you have another differentiation. Okay, so we are almost at the end of this, and I have similarly the component Ryy, which is again a nonlinear wave equation. But now it's for capital A. And I will just do the same, just to claim that the principal part is rho a t minus rho minus 1 a theta equal lower order terms. This equation again is satisfied in a distributional sense. So this is satisfied in W minus 1, 2. And we have, so I wrote this component. So there is now, next component that comes is Rxy. Okay, and this component is a wave equation, but now for the area function. Okay, so it's the same operator. You have rho r t minus rho minus 1 r theta theta equal lower order terms. Okay, and now this is an equation that you write in w minus 1 infinity. You have more regularity on RT than you have on AT or PT. Okay. So this is basically the end of the derivation of the set of PDEs. There are a few more pages that would show you the details of the derivation of these final equations. But otherwise, we have the structure of the Einstein equations on the blackboard. We have nonlinear wave equations. There are a number of lower order terms that, of course, we cannot neglect. And fortunately, it's not completely, messy because we have been able to identify some quantities that are actually conserved. Okay. So these four equations here correspond to the so-called twist coefficient, conservation of the twist coefficients in space and time. So you have the proof of that, the fact that these equations are very simple and conserve some quantities. This is actually done geometrically in a section before that I show you. So you have such a statement, and you have this system here. And of course, everything is coupled, right? Rho is coupled to, all these equations are coupled. You cannot solve them independently, except for the ones where you say some quantities are conserved. Of course, you can integrate out this in theta or this one in t, and get some first integrals. Okay, so we arrive at the end of this discussion. I'm not going to tell you more about the details of that, but the calculations are not so straightforward. Okay, actually, I realized that I was forgetting one component. So here it comes now. So you have one more component in a z direction, which starts the same way, rho, nu t. Right, it's the same on nu, right? T minus rho minus 1, nu theta, theta. And if you look at the other terms, they are again quadratic products of first derivatives. Plus a term that is just algebraic with no derivative. So you can think of them as being lower order. And this equation is satisfied in W minus 1 sense. Okay, we should conclude now that what we have found is 4 nonlinear wave equations. So 1, 2, 3, 4 here. We have essentially ODEs to supplement this set of equations. And so our goal now will be to solve that at a weak regularity level. So even a small time existence theory is something that is not obvious. There is a lot of work to do to obtain this. So this is what we will do next. Introduce the techniques of functional analysis, so in the next 2 chapters that will be relevant to work with weak solutions in suitable functional spaces. The choice of gauge will come because what I wrote on the blackboard, on the screen, were just admissible coordinates, or general coordinates that use a symmetry, but that's not enough. You want to be a little bit more specific about how you choose the coordinates in order to get something tractable. So we will do that. We will introduce conformal coordinates, areal coordinates. So this will be the first issue, how to get local in time existence of weak solutions. And then, of course, will come the question of what is a global geometry of these spacetimes. Right? So you want to say something more about global causality conditions in a spacetime. And to finish with this chapter, let me emphasize that what I presented is a very robust framework that applies with other symmetry assumptions, like spherical symmetry. It also is robust in the sense that it allows for matter to be introduced. So it's not difficult if the matter is smooth, does not introduce additional singularities, but it's more tricky if you have a compressible fluid. But essentially it goes along the same lines. And so what I will focus on now are the techniques of analysis to prove local existence, global existence, and that's what we are going to do now. So we continue with this chapter on the Cauchy problem, where we are going to exploit the gauge freedom in order to simplify the Einstein equation. So they look reasonable, these equations, but still if we could simplify them a little bit more, it's going to be easier, I mean, to be better, right? So we need to introduce coordinates that are adapted to the problem. So two things, conformal coordinates that are basically null coordinates, and areal coordinates where the time function will be related to this function r. The time function will be chosen to be capital R. Okay, and you will see why this can be done. To proceed, we need to specify what functional spaces we will work with. So since we already have spaces associated with these various quantities, of course we can guess that P will look for it in H1, and A in H1, and R in W1 infinity, and U in W11. But we need to find the correct energy estimates that reflect this regularity. At this moment, this is a regularity that I have decided. Only my motivation at this stage was, in some sense, only to give a meaning to the Einstein equations. Right? So we know that we can give a meaning to the Einstein equation at this level of regularity, but now we need to produce the energy norm, monotonicity argument, compactness argument, continuation principles that will allow us to obtain the local existence theory. And so this is how we proceed now. We look at the conformal and areal gauges as a way to simplify the set of PDEs that we have on the blackboard. And then we will have the main technique of constructing Cauchy developments for Ricci flat spacetimes. And we will realize that, so the idea of the areal coordinates is that you can arrange the time function. You can arrange the time function in such a way that on each slice, the area, this function R that we define in the spacetime, right, according to the symmetry assumption, we know that there are T2 orbits. So we look at this, the area of these T2 orbits, and we can arrange the foliation in such a way that this R remains constant on the slice. Right? So this is a way that we will foliate T equal constant, and we will choose the time function to coincide with this quantity. And in practice, if you think of the global geometry, what will typically happen is that R will go to infinity in a future direction, and R will go to 0 in the past. Okay. So we will have, in one direction, we will have an expansion forever, and in the other direction, if we go to the past, we will have a contraction where this area is shrinking to 0. Okay. So that's a choice that is the right one. I mean, this is a choice that you want to make in order to describe the global geometry. But before we can do that, we have to do local analysis in conformal coordinates. And I put in the last section a number of elements of proof that I will probably not have time to present, but again, all the details will be in the documents that you can download later. Okay, so here we are. So we start with a weakly regular T2 symmetric spacetime with coordinates T, X, Y, theta, admissible coordinates. We assume that the time function varies between two bounds, T0 and T1. So we are, if you like, we are taking a piece of a space-time that So this is S1, the topology here, this is S1. And so we take a part of the spacetime where the time function has not yet been chosen to coincide with the area of the orbits of symmetry, but we have two slices, tau 0, tau 1, and we look at such a region of the spacetime, and we want to find arguments to solve the Einstein equations in such a region. And the first question is whether we can find conformal coordinates, right? Admissible coordinates, this is something that is given by the symmetry and the decomposition that we have made. So the first question is whether we can find conformal coordinates. So conformal coordinates are defined in this way. So they allow you to rewrite the metric in this form, E2 nu minus 2p over r times minus tau squared plus dig psi squared. So this is the metric of the quotient. Maybe I should also put it on the blackboard. I could probably erase this side. Okay, so what I'm claiming now is that we can choose coordinates, which are called conformal coordinates, in which the matrix takes a slightly simpler form compared to before. And the form that I want, if I look at the quotient metric like this, I would like the metric to be of the form E2 nu minus 2p divided by r multiplied by minus d tau squared plus d psi squared. Right? So if you like, I mean, this is really the flat metric, and there is only a conformal factor in front of it, depending on some coefficient nu and p, in order to get the space-time metric of the quotient. Okay? And the rest has not changed here. The rest is kept in this form. Okay? So we still have to look at coefficient u, p, a, r, g, and h exactly like before. And we will do that in such a way that the hypersurface, so you remember that we are working in between two slices. So we are interested in mapping a domain like this to a new domain, where we will keep the initial slice. So the initial slice will be the same in both system of coordinates. That's what is meant by this condition, that the hypersurface t equals t0 coincide, t equals t0 is chosen to coincide with the other one that I call in the variable tau equal tau 0. Okay, and so I'm taking the same, somehow the same coordinates here, but I'm changing the coordinates in the future. So we'll do that in such a way that the new coordinates tau, psi, x, and y determine a global chart on our manifold, or the piece of the manifold, if you like, that we are looking at. And they will define the C-infinity differential structure. So it means that you can do change of coordinates with a C-infinity regularity, even though this chart, t, tau, psi, and theta, and t and theta, will be only W1 infinity compatible. Okay, maybe slightly more regular, but they are not C-infinity compatible. So the functions, one coordinate function with respect to the original coordinates, this mapping is not smooth. Okay, has a limited regularity. That's expected, right? Because our metric has a limited regularity. So, okay, so I need to explain this, right? So I need to discuss that a little bit more to convince you that this is possible, and that this is possible at the level of regularity that we are working on. Okay, so you see what we want to achieve, and as I started saying on the blackboard, we only look at the quotient metric, so you can somehow forget about the dx square and dy square in the expression of the metric. And what we would like to do, we would like to find functions tau and psi in such a way that the metric, which originally was written in the form E2 nu minus 2p over r times minus rho squared dt squared plus d theta squared. So we would like to express our metric in this form. And I need to put a hat on this nu, on this variable nu here, which is going to change in the transformation. Okay. But the form globally, the form is the same. I have a new function nu hat here, and I have changed the form of this metric, which now I would like it to be the flat metric. So the relation between nu and nu hat is going to be specified in a minute. So we would like to get null coordinates. So to do that, we will first construct null coordinates. These null coordinates u and v will be functions of t and theta of our given coordinates. So we look for two functions, u of t and theta and v of t and theta. And we will choose them in such a way that u sub t plus rho u theta is 0, and v sub t minus rho v theta is 0. So this is a system that we are going to produce this decomposition. We are going to solve this system. Right? I mean, this is not difficult. It's just an issue of regularities that you have to do that by making sure that all the regularities that you have assumed is sufficient to do the construction. Right? So the null coordinates are defined by this system. You know that in space we are working on S1, so we should impose some periodicity condition. And the periodicity condition at the level of the functions u should be this. So u of theta plus 2 pi should be u of theta minus 2 pi. And v of theta plus 2 pi should be v of theta plus 2 pi. So this combination is just done. You will see in a second why it is 2 pi or minus 2 pi. But the philosophy is that it has to be periodic. For some reason, there is a constant that you have to add or subtract here. But basically, it says that these functions are 2 pi periodic. And also, the regularities that we expect is that this mapping uv are only w1 infinity functions. Okay? And this should be a diffeomorphism, or at least on the image, because we will not map the whole region. We will map a neighborhood of the initial slice, which is enough for the construction of these coordinates. So of course, if we have solved that and we have constructed null coordinates, we can recover what we want simply by deciding that psi is u over 2 is v minus u over 2, and we will set tau is v plus u over 2, and you can check easily that these functions satisfies our requirement and give us the decomposition that we want. Okay, just a simple algebra. Okay, so we need to find these functions. Maybe in passing, you realize that the connection between u and u tilde is this, right? So what's interesting is that nu is only w11 and u theta. So you have to be careful about the regularity and make sure that the regularity is preserved in the transformation. And all the spaces that we have will be okay. Maybe I return to that after we have a little bit more material. Okay, now for the existence of the null coordinates, we proceed in the following way. We have an interval of time t0, t1, and we choose for u and v on the initial time, on this initial slice, we take some prescribed value for u and v. So essentially, we are saying that u is minus theta plus a constant, and we are saying that v is plus theta plus some constant. Okay. Of course, it's not unique, just a way to normalize, to define u to be decreasing and v to be increasing on this initial slice. Just one possible choice. And now what we are doing here, we are now integrating, we follow characteristics for this linear system, actually we have two speeds for the characteristics. I mean, one positive, one negative, corresponding to this speed rho and plus rho and minus rho. So we introduce the corresponding characteristics line by integrating this system. So we have function theta of t, so theta bar plus of t. This is a trajectory from an arbitrary point here in time, and we have something analogous from the same point. We define a theta plus and we define a theta minus by simply following these curves at the speed which is given by rho. And you remember that rho is W2 infinity, or at least 1 infinity is what we are using essentially here. So rho being Lipschitz continuous, so in fact slightly more regular. By standard ODE, we do produce existence. We have the existence of solutions for these trajectories. They are Lipschitz continuous. And we can also look at the theta derivative of these trajectories. You have a classical formula for the variation of a solution of an ODE with respect to the initial point. So it's given by an exponential of derivative, rho theta over rho, at a suitable point. Of course, this never vanishes, and therefore you see that the maps that you have defined remain diffeomorphism, at least on their image. So that's what you want. And so everything here is done with a Lipschitz regularity, and it works nicely. And then you solve the hyperbolic equation simply by putting theta bar plus or minus. Here. So periodicity is a consequence of our construction, but the main point is that now you want to recover the null coordinates. You want to define the null coordinates, and you define the null coordinates by solving this system of two equations along the characteristics plus rho or minus rho, which I have introduced, and therefore the formula is simply that U remains constant along the characteristics given by that. But now you check that the regularity, so maybe that's the main point, I mean, of all of the story, is that in this construction, the fact that we had weak regularity and only W1 infinity regularity for rho is actually enough for the definition of the characteristics and the construction of the null coordinates. And the fact that rho is actually W21 allows you to check that the regularity of nu, which was W11, is preserved by the transformation. Okay? So by looking at the regularity of each term, you can check this easily, that the regularity is not changed by this transformation. This transformation exists, regularity remains the same, the weak regularity. Okay. So we can proceed. We have conformal coordinates, and now instead of the form of the matrix that we had before, we have something slightly simpler now. So how simple is that? How simple it is? So look at the formula here. So basically what we have obtained, what we have achieved, is that the factor rho that came here, this conformal factor, is taken now to be 1. So that was a nice simplification in the equation. And what I'm writing now is simply the set of equations that I wrote schematically on the blackboard, where rho is taken to be 1, t and theta now are called tau and psi. And because now it has simplified, the expression have simplified, I can write all the terms in a rather compact form that you see here. Okay. So you have wave equations. You have quadratic terms here, quadratic products of this form, like so. So these are something that are called null forms. And here the wave equation for R contains an algebraic term here. And you have again null forms here and an algebraic quantity for the wave equation for nu. Okay? So this is a system for which you have to prove a local existence result. So this will be good to say that the Cauchy problem, there exists Cauchy developments of an initial data set. But these coordinates are not going to be useful if you want to analyze the global geometry of the spacetime. Okay. So we will do that with a different choice of coordinates. Of course, if you want a full system, you cannot forget the constraints. There are 4 constraints. So 2 are rather easy. There are 2 auxiliary equations as well here. So the 2 main constraints are these first 2 equations, which correspond to what I erased on the blackboard. But there was this equation with r psi psi, and there is here an equation with r psi tau. So these 2 terms correspond to the term with the largest number of derivatives. And the other terms are in L1. So I can again repeat the observation from before, that from these 2 constraint equations, you can deduce an additional regularity for r psi psi and r psi tau, which is that these 2 quantities are not distributions, but they are actually in L1. Okay. So I have a little bit more time to show you also the equations in real coordinates. So this will be the second choice of coordinates that we will need to make. As I said before, we now would like to have a time function coinciding with the area of the orbits of symmetry. And why is this possible? So this is possible because nabla r is a timelike vector. So if you look at the area of symmetry, this quantity in a timelike directions is increasing or decreasing. It has a monotonicity in this direction. So it's rather natural to use it as being the time in your manifold, and this is something that you can do globally. Okay, so I'm going to emphasize to prove this property in a minute, and especially prove it at the weak regularity level. Of course, if you are able to do that, right, to decide that r is equal to t, of course there is no issue of regularity because it's obviously c infinity if it's just t, just a coordinate. But now the conformal metric, which instead of rho, I'm going to use a different notation a below, but it has the same meaning to be the coefficient rho. This rho now has only some limited regularity. You cannot, you cannot prove it better. I mean, you could. I mean, there are limitations on the regularity of the coordinates that you can introduce. So if you decide to have a rather or very nice time function, then this conformal metric is much less regular. Okay, so we need first to revisit the regularity of R. So this is something that, so what I state here is essentially something that we already observed. So the function R is W11 in space, R sub t is 21, R sub t is W11, and RTT is in L1. So how do we get that? So we get that simply, as I mentioned before, the constraint equations give us a control of 2 derivatives, theta theta of R. The derivatives R theta t is also controlled by another constraint equation. So that give you part of the statement of regularity here. And the final statement comes from the evolution equations, because we have also a wave equation for R. So if you have a nice 2 derivatives in space which are nice, of course the 2 derivatives in time have also to be also nice by using the wave equation. Okay. So all of these terms are nicer than we expected in the beginning. And this is specified in these spaces here. Now you would like now to have an argument to show the existence of areal coordinates. And so what I will show now is that at least if the manifold is not flat, because if the manifold is flat, right, just the trivial situation of empty flat manifold, of course this R would be a constant and there is no possibility to use it as a time function. But as soon as your manifold is not just identically the Minkowski space, then the vector field, nabla R, turns out to be timelike. Okay. So the area is going to be increasing or decreasing when you go to the future or you go to the past. And we will use it as a time function. Okay, so here's the analysis of the norm of the gradient. Nabla R in principle is only L infinity, right? That's what was given to us by the definition, the geometric definition. And then we observe that it was actually more regular. So nabla R was, in fact, absolutely continuous. And so it's continuous, and that's good for the arguments that we want. So now we look at this nabla R, and this nabla R is defined everywhere. It's a continuous function on the manifold. Okay, and so to prove that, this property of the gradient, we return to the Einstein constraints. So the Einstein constraints turns out to have this form. So you can see that step by step, you extract some structure of the equation. The equation looked very messy in the beginning, and then step by step you realize that there are some quantities that can be integrated. And so this is another very nice argument that if you define lambda plus minus to be this quantity, right? So you look at the derivative of the area, you multiply by this conformal factor rho plus r theta, and you look at both possibilities, both signs. If you also introduce this quantity, capital H is nu theta minus p theta plus rho nu t minus p sub t. Okay, so you introduce these two functions, and you look at the Einstein constraints, right? The two Einstein constraints that look quite long and quite complicated before. And then they turned out to have this very nice form that the theta derivative of each lambda plus and lambda minus is equal to lambda plus or lambda minus. And then what is left are, for each equation, there are two equations, and each of them contains the same h, this quantity here, and it contains also the same n. I'm not writing the expression for n, because it contains quadratic quantities. It contains basically terms like pt square and at square and terms of this form. And the point, it's a sum of squares. And the point is that it has a sign. So you have this structure. N is L2, or actually it may be L1, in fact. But it doesn't matter for what I'm writing here. I think it's L1. But so you have this structure, right? So if you have this structure in theta, you will, you should see how it comes, right? Because here you differentiate in theta. I really would like to make this clear. Yeah, from here, right? So what I did, actually, what I do, I take the two constraint equations here, these two equations, and I look at the highest derivatives, arc psi psi and arc psi tau here. And what I do is that I compute the sum of that. If you compute the sum, you will get one of the two of these two functions, basically appearing. And if you compute the difference, you will get the other quantity with, say, a negative sign. Okay, you see the structure, and all the other terms would be squared. I mean, it's not completely obvious from that, but it's just a direct calculation. So this is a structure. You sum the two Einstein constraint equations, the non-trivial ones. You get this structure, and so okay. And so now you integrate, right? So you see that you have theta derivative. So you can integrate. So you get an expression like this. I guess, yeah, maybe the time is almost over. So I just finished with this page. So you integrate with respect to theta. So you get the integral from any theta 0 that you like, that you fix, to theta of an exponential factor times n. N is positive. And then you look at the expression here, And so you can look at the details to understand completely the argument, but the philosophy of the argument is that this cannot vanish because it's an integral of positive quantities and exponential, so it's not going to vanish. With the periodicity of R, you can show, so it's not, you have a small calculation to do to see that, you can show that you cannot have both of them positive or both of them negative. I mean, this is actually the key part of the argument, right? Okay, so why not? Because if they are both positive, you return to the definition and you say, okay, these two quantities are positive, and then the sum is positive, and then R theta, or 2R theta is positive, so R is increasing, but it's periodic, and so it cannot work, except if it's trivial. Okay, so you exclude that, and if you exclude that, it means that the product is negative. And if the product is negative, it's exactly the statement that the gradient of R is timelike, because the norm of the gradient is a product of these two quantities. Okay, and then there's the final case where n would be identically 0, and you want to conclude that the spacetime is flat. And so, of course, you have now to know what capital N is. So I told you it's a sum of squares, right? So if it is 0, it means that each term is 0, and it gives you a lot of things that U and A are actually constant, because this involves the derivatives of U and A. So they are constant functions in space and time. Capital K is 0. Capital K is a twist, a so-called twist constant. And these GH are constant, but they are irrelevant. And you are left with only one coefficient nu, and there is a final argument to go from a trivial flat wave equation for nu. You solve it, so nu is a sum of a function of u plus a function of v, where u, v are null coordinates. You put it here, and you realize that you just have the flat metric left. Okay? So I think it's a good place to stop, and next time we will do the analysis of the Cauchy problem. We'll take this big system in conformal coordinates, solve it for a small time, and in some suitable energy norm, and when we will have arguments to construct in areal coordinates to construct a global foliation, and later on we will analyze the asymptotics of that.